So we have another operation which doesn't actually exist in our normal operations of numbers. And you're going to find very quickly we actually have two multiple types of multiplication in when our elements are vectors or matrices. We have what's called scalar multiplication, and then we have what's called vector or matrix multiplication. So in this video, I'm going to discuss scalar multiplication. And for those of you with a background in abstract algebra, you'll recognize this very quickly as what we refer to as a group action, but I'm not going to hold that interpretation, or for you to know that interpretation if you have not had a background in abstract algebra. But with that stated, scalar multiplication also is another very easy type of operation to learn. Here's the idea. If we have a matrix A and a number K, an actual number, not a matrix, just a number, then the way that we define the scalar multiplication between the two is as the matrix K times whatever element is in A11, K times whatever is in A12, K whatever is in A1M, same deal, K, if I have an N, if A is N by M, K times N1, K, N2, and then K, A, N, M. Okay, so basically we just take the number and multiply it throughout the matrix. So that's how we define scalar multiplication. So the way we construct our new matrix from the number A, the number K and the matrix big A is as another matrix, Cij, where that's just defined as the product between the number and then the element Aij. So for example, suppose I had the matrix excuse me, 1, 2, 4, 5. Okay, I can construct a new matrix where basically I distribute this to all of the elements. So 3 times 1 is 3, 3 times 2 is 6, 3 times 4 is 12, 3 times 5 is 15. Okay, so we have our second basic operation. And oh, by the way, you can go the other way. So suppose I had the matrix 6, 18, 21, and 3. You'll happen to notice that all of these numbers here are divisible by 3, right? This is the same thing as saying 3 times 2, 3 times 6, 3 times 7, and 3 times 1. So what you can actually do is reverse the process. If you happen to notice that there's a value which can go through all of them, you can actually pull that out. So this is equivalent to saying 3 times 2, 6, 7, 1. And it doesn't need to be integers, by the way. For example, I could have something like 5, 6, 2, and 3, and I can pull out a 3. And that's the same thing as saying 5 over 3, 2 over 3, and 1. Right? Because what do you get if you distribute this? 3 times 5 over 3 is just 5. 3 times 2 is 6. 3 times 2/3 is 2. And 3 times 1 is 3. So you can distribute out numbers in front of the matrix, or you can pull them out of the matrix. And by the way, the same works for vectors. And we're going to actually see that addition and scalar multiplication have very specific types of meanings behind them geometrically, and we'll learn that soon. But anyway, so you can actually represent this same deal, right? 3 seconds and 2. And you'll notice if you go the opposite way, 2 times 2 is 4, 2 times 2/3 is 3, 2 times 1 is 2. So you can go back and forth between the two.